Imagine this. A ripple, maybe, a pattern, writing itself through matter. It's not quite a solid thing like a marble, but it's not just fog either. It's something, well, something in between. Something that really won't sit still in our usual boxes. This is kind of the world Erwin Schrödinger opened up for us. He gave us this equation, incredibly precise, predicts atomic behavior, spectra, all sorts of things with amazing accuracy. And yet the equation itself was so profoundly weird, it kicked off a whole century of arguments about what reality is. So today, we're doing a deep dive into Schrödinger's work, his equation, but we're looking at it through a really different lens, motion theory. Now, this isn't about finding new physics, okay? It's more about fundamentally restoring what we already know, giving a new meaning to the math that, well, works unbelievably well. It's like we've had this amazing car engine all along, but maybe, just maybe, we're finally getting the right user manual for it.
Exactly. And what's really fascinating, I think, about motion theory is the idea that Schrödinger didn't just find a mystery. He actually uncovered a universe built on structured motion, and that structure just needed a better story, a better narrative. So our mission in this deep dive is really to unpack that, to help you see what it means to view everything as, quote, structured motion synchronizing under constraint. What does that mean? Well, things like space, maybe that's just unresolved motion. Time, maybe it's just how we measure movement. Even fields could be seen as basically motion gradients. The question we always come back to is, what is the motion doing?
Okay, so let's ground this a bit. Schrödinger himself, 1926, right? He gives us this non-relativistic wave equation, and it was huge. A monumental achievement. It treated tiny things, electrons, as wave-like. It explained why they stick around atoms in certain ways, predicted the hydrogen spectrum, and it just immediately agreed with experiments, which is, incredible for the time. But, and here's the big but, the success, the very power of the equation, it also led to these really unsettling, mind-bending implications, famously highlighted by Schrödinger himself, wasn't it, in 1935 with that thought experiment, the one with the cat.
Ah, yes, the cat. Poor thing. It was a brilliant move, though, a reductio ad absurdum, basically showing how extending the logic leads to something absurd. He was pointing right at what we now call the measurement problem. See, the equation itself, it evolves smoothly, linearly, but that seemed to suggest systems could exist in these macroscopic superpositions, meaning for the cat, it could be somehow simultaneously dead and alive until someone looked.
Right, which is just bizarre.
It is. And the mainstream interpretation, this sort of standard way of dealing with this, says that the wave function, which is seen as this complex probability wave, it just sort of collapses. It collapses into one single outcome the moment you measure it. But let's be honest, that collapse always felt a bit like magic. Like a gap in our understanding.
Yeah, like the universe just snaps to attention when we look. It doesn't feel quite right. So this is where motion theory steps in. It doesn't change the math, you said. Schrödinger's brilliant equation stays. But it changes what the symbols mean. It keeps the engine, rewrites the manual. So instead of that fuzzy probability cloud, what is the wave function in motion theory?
Precisely. That's the core shift. Motion theory sees not as some physical misspreading out, but as an alignment functional. Think of it more like a detailed blueprint, or maybe a musical score. Yeah, a score for how the system's internal movements could potentially harmonize, how they could synchronize. It's an alignment ledger, really, keeping track of all the possible ways the structured motion could configure itself. It encodes what we call phase compatibility, which is basically how easily the system can find its rhythm, synchronize along each path available to it.
Okay, a harmony blueprint. Alignment score, I like that. So if P is the score, what about its amplitude squared? Traditionally, that's the probability, right? Probability of finding a particle here or there. Does that change too?
It absolutely does. It's not just probability anymore. Measures the availability of stable synchronization given the system's current constraints. Think of it as how likely a particular rhythm or harmony is to actually resolve and become stable within the whole system, the ease of finding that stable sync. And the complex phase, that imaginary part of that often seems mysterious, that tracks what we call ordering tension. It's the dynamic push and pull, the potential for things to either fall into sync or fall out of sync across all those possible configurations. So this gives us a completely different way, and I think a much more intuitive way, to understand these classic quantum effects.
That feels like a really significant shift. Okay, let's test it. Take superposition. Classic example, often described as, a particle literally being in two places at once. How does this alignment score idea handle that?
Right, the two places at once thing is catchy, but maybe misleading. If we think in terms of motion and alignment, superposition means something different. It means that before a definite constraint is applied, before the system has to commit, It can support simultaneous partial alignments along multiple motion pathways. We call these pathways sync corridors. Imagine maybe a dancer exploring several potential next moves almost at the same time before smoothly transitioning into one. That's why we see interference patterns in experiments like the double slit. It's one structure, one coherent motion, effectively sampling multiple sync corridors before a final resolution forces it down one path.
Wow, okay. That makes so much more sense visually than trying to picture one electron going through two separate slits. It's sampling the possibilities. So if that's superposition, what about the collapse? That sudden moment where the possibilities vanish and we get one reality. Does collapse still happen? Or do we ditch that word too?
We reframe it. Collapse becomes enforced resolution.
Hmm.
Think about a measurement device, a Geiger counter, a camera sensor, whatever. It's not just passively watching. Fundamentally, it's a high-gain feedback structure. It's an alignment amplifier. So when the sensitive device couples to a system that's in superposition, exploring multiple sync corridors, it rapidly forces a kind of global resynchronization. The whole system, including the detector, quickly settles onto a single, stable pathway. The apparent jump, the discontinuity we see, isn't magic. It's just a very fast motion rephase. The system quickly finds the most stable rhythm available under that new, strong constraint imposed by the detector.
A fast rephase, not a magical collapse. I like that. That feels much more physical. Okay, this is really clarifying. But if motion theory reinterprets everything, where does Schrödinger's equation itself come from? It works so well, it has to emerge from this motion picture somehow, right?
Absolutely, and this is one of the really elegant parts. We can actually rederive the Schrödinger's equation starting from what we call motion-native quantities. Things like motion intensity, resistance to motion, the pressure to synchronize, the degree of alignment. These are the fundamental building blocks. Then we impose a principle like action minimality in phase space, which basically means the motion tries to find the most efficient path, the path of least resistance, you could say. And if we look at the limit where things are changing gently, the small amplitude, slowly varying limit, the underlying equations, the Euler-Lagrange equations, they naturally simplify, they linearize into the Schrödinger equation.
So it just falls out of these basic motion principles.
Pretty much. And what's really neat is that the imaginary unit pops out naturally in this process. It's not just put in by hand. It captures the essential quarter-cycle phase rotation needed for the kind of smooth, continuous evolution, unitary evolution that quantum systems undergo. It's like the fundamental timing, the rhythm keeper. And Planck's constant, that stops being just some random small number the universe uses. It emerges as the minimum stable motion action per cycle. It's the smallest possible chunk of rhythm, the smallest stable unit of coherent change that allows alignment to happen. Below that, things can't quite close the loop and stabilize.
Okay, so the equation itself becomes a description of these underlying motion dynamics. What about the terms within it, like the Hamiltonian h hat, usually representing total energy?
Right, the Hamiltonian H. In motion theory, that becomes the operator that computes local reordering pressure. Think of it as calculating the local stress or effort involved in maintaining or changing the alignment pattern, the kinetic energy term. That relates to the curvature of alignment, how much the motion pattern is bending or changing shape, and the potential energy term. That corresponds to stored mismatch, basically, how much the system is out of sync or contains unresolved tension. So the whole Schrödinger form just emerges as the natural way to describe the linearized alignment flow of structured motion. We keep all the predictive power, but the symbols now tell a story about motion and rhythm.
Let's make this even more concrete then. Apply it to some classics. What about, say, an electron and a hydrogen atom? We learn about orbits, energy levels. How does motion theory see these bound states?
Yeah, the old picture is like tiny planets orbiting a sun. Motion theory offers a different view. The hydrogen spectrum, all those sharp lines of light it emits, they arise from the allowed standing alignment patterns around the nucleus. The nucleus isn't just a central point charge. It acts as a high-density sync attractor. It pulls the electron's motion into specific, stable, resonant rhythms. And the quantum numbers we use, N, L, M, they simply label the different ways these patterns can form, their shape, their complexity, the number of nodes, like different ways a violin string can vibrate to produce distinct notes.
A standing wave of alignment. That's a much richer image. Okay, now the really tricky one, entanglement. This is the one that Einstein famously called spooky action at a distance. Particles linked mysteriously, instantly affecting each other over vast distances. How does motion theory explain that without the spookiness?
That's always the big question, isn't it?
Yeah.
How can it not be spooky? Well, motion theory suggests entanglement isn't about sending secret messages faster than light. It proposes that entangled particles are, quite literally, born from one structured motion. They originate from the same event, the same initial synchronized state.
Yeah.
Because of this shared origin, they maintain a shared alignment ledger, even when they fly apart, separated by what we call space, which, remember, is also seen as motion. They remain connected through this single shared history, this shared score. There's still fundamentally parts of one unified motion system described by that single ledger.
Until
Something measures one of them. Exactly. Until something locally forces an incompatible resolution on one part of the system. Because they share the ledger, resolving one instantly influences the possibilities for the other, constrained by their shared history. So the weird correlations we see in Bell tests, the violations of local realism, they aren't signals traveling faster than light. They represent the co-resolution of a single ledger. When you measure one particle with a certain setting and the other with another setting, you're basically asking the entire shared system which alignment pathways can simultaneously stabilize under those specific complementary constraints. The statistics just fall out from that co-resolution.
no spooky forces, just one shared history, one ledger, resolving itself globally when poked. That actually makes a strange kind of sense. Okay, let's loop back to measurement then, and the cat. You said the detector is an alignment amplifier. So what is actually snapping when an observation happens? What goes on inside that Geiger tube from this perspective?
Right. The Geiger tube, or any detector, it's built to be sensitive. It has enormous gain. Tiny inputs trigger big outputs, and strong memory. It latches into a state. Plus, it's strongly coupled to its environment, allowing it to quickly dissipate energy and stabilize a result. So when this highly sensitive high-gain device interacts with a system in superposition, exploring multiple sync corridors, the combined system detector plus particle, it very rapidly rephases. It snaps into a single stable alignment corridor because that's the only way to maintain overall stability and maximize the alignment under the detector's demanding constraints. It finds the easiest, most stable joint rhythm. The cat was never actually two cats, one alive, one dead. The whole setup represented a potential untestable many-corridor plan. Once the trigger fires, the feedback forces a resolution to just one executed corridor. It's a forced decision, driven by the physics of amplification and stability, not by conscious observation.
That takes the magic out of it, makes it a physical process.
Okay, this whole restoring feels really powerful. Thinking about Schrödinger's legacy now through this motion theory lens, what's the biggest takeaway? How does it change how we see his contribution? Well, first, Schrödinger brilliantly unified dynamics with a single equation, a single generator. Motion theory really honors that by showing how one underlying principle, this alignment flow, can account for so much, from atoms to optics. Second, he really highlighted the map territory gap. He showed that tau, the map, lives in configuration space, a space of relationships between modes of motion, not just our ordinary 3D space, the territory. Motion theory embraces that, seeing reality as this interplay of motion modes. And crucially, he forced the measurement problem out into the open. He made it impossible to ignore. Motion theory addresses it directly. We keep the smooth evolution as alignment bookkeeping, and we replace the mysterious collapse with this physical process of enforced resolution.
It feels like a more complete picture. You mentioned it's not new physics, but could we actually test this restoring? Are there experiments that might favor this interpretation over others?
That's a great question. And yes, potentially. We could think about designing experiments differently. For example, a phase index double slit experiment. Imagine putting a special film over one slit, a film whose motion index, its resistance to alignment flow, could be tuned. Motion theory predicts specific shifts in the interference pattern based purely on this alignment curvature, not just standard phase delay. The numbers might be the same, but the reason would be clearer, more direct. We could also explore weak measurements. These are gentle probes that don't fully collapse the system. We could use them as ledger probes to try and track that alignment ledger while it's still exploring multiple corridors between setting it up and making a final strong measurement. Motion theory would predict seeing smooth corridor weights, reflecting the dynamic alignment tendencies, rather than just probabilities popping out at the end.
Fascinating. And what about those other persistent questions people have? Like, where do probabilities come from if it's not fundamental randomness? Or why on earth do we use complex numbers with IA in physics?
Right, motion theory offers direct answers there, too. Probabilities, they aren't fundamental coin flips. They emerge from relative corridor stability. Given the system's constraints and limited resources like energy, some alignment pathways, some rhythms are just more stable or easier to maintain than others, the probabilities reflect that relative stability, like water favoring the path of least resistance down a hill. Why complex numbers? Because alignment, synchronization, It's fundamentally about phase relationships, which are rotations. The imaginary unit I is the natural mathematical tool to describe rotation, specifically the quarter-cycle orthogonality between the flow and its driving gradient. It's essential for capturing how these rhythms evolve coherently. And Planck's constant, as we said, it's the minimum stable rhythm. It's the fundamental beat, the smallest unit of action exchange needed for a stable repeating pattern for alignment to actually lock in. Below that quantum limit, you just get noise, no stable structure.
It really is like getting a new dictionary, isn't it? Translating the old words.
Exactly. We're translating the legacy labels. Potential energy becomes stored misalignment, tension waiting to resolve. Kinetic energy is alignment curvature flow, how the rhythm is changing. Mass is effectively motion resistance. Charge describes a kind of motion imbalance and how it wants to redistribute to find sync. And the field is just a motion gradient, mapping out the intensity or direction of the underlying alignment flow across space. The equations that work so well remain, but the story they tell changes. It stops treating the mathematical map as the territory and starts describing the actual territory, the structured motion itself.
What an incredible deep dive. Taking Schrödinger's amazing work and seeing it through this lens of motion theory, it genuinely offers a clearer, maybe more intuitive way to grasp the quantum world. It feels like you can walk away from this with a completely new perspective.
That's the hope. Schrödinger gave us the engine, the mathematics that describes how matter sings. Motion theory aims to keep that beautiful engine, but reveal the actual stage it performs on. This dynamic world of structured motion, constantly weaving patterns of alignment under constraint.
So maybe the picture to leave with is this.
The wave function isn't fog, it's the musical score. Superposition isn't indecision, it's the orchestra, auditioning different harmonies. Measurement isn't magic, it's the conductor's downbeat the moment the orchestra commits to playing one specific tune. And time. Time isn't some river flowing past us. Maybe time is just a measure of how fast the music resolves.